Hi, I'm Steve Jiang. I'm the Vice Chair of the Department of Radiation Oncology at UT Southwestern. I'm also the Director of the Division of Medical Physics and Engineering in the department. So today I'll talk about the AI research at UT Southwestern Radiation Oncology. So in our division, we have 30 faculty physicists on one campus, and we're hiring two more. And most of us have both clinical and research duties. Our research are in two major directions. One is preclinical technology research, like animal imaging and treatment. And the second one is artificial intelligence. So we are trying to establish a preclinical radiation research center together with our molecular radiation biology division. And we currently have about $15 million funding in this research direction. But today I want to focus on artificial intelligence research in our division and department. So the AI research is mainly carried out in medical artificial intelligence and automation lab, Maya lab, which was established in July 2017. Currently, we have about 10 faculty members and about 40 students, postdocs. Our mission is to empower clinicians, especially those with less experience or limited resources, for improved patient care by innovating, developing, and deploying AI in radiation oncology and medicine in general. So we try to improve accuracy by retrieving hidden information from patient data, images, and performing better, hopefully, than most physicians when there's a ground truth. We also try to improve the efficiency by automating clinical procedures and by saving physicians' time in front of the computers. And the third uh, part of our mission, which we think is also very important, it might be even more important than the first two, that is to reduce the healthcare disparities by transferring expertise to less experienced physicians through the learning of AI from experienced physicians. So in radiation oncology, uh, we pretty much can apply AI at every step of the clinical workflow. So we have done a lot of work involving every step of the workflow, but here I will focus on a few examples. One is medical imaging segmentation, which is a very popular AI research area in medicine, in Redang too. But in our group, we have focused on the auto segmentation of challenging organs and also the GTV and CTV, gross tumor volume and clinical target volume. One project is the CTV segmentation for post-op prostate cancer patients. In that case, prostate gland has been surgically removed. The residual tumor cells are not visible in CT or MRI images. And there is not an object with the well-defined boundary by image contrast to segment. So therefore, it's very challenging for AI and also for physicians to segment, to delineate CTV for those patients. And of course, there are clinical guidelines such as NRG, and also there are factors like the relationship with nearby organs, like the pathology report, pre-op MR images, and the individual patient characteristics, and also the variability in anatomy and communities. Those things can be considered during the segmentation. However, there are still large variations among physicians because on top of the clinical guidelines, there is still a large room for individual physicians to practice their own judgment based on their training background, their experience, their personal preference, instinct, and so many subjective factors there. So we actually looked at about 400 patients in our department, and we developed an AI, specifically the deep learning classifier, that is to use each physician's name as the label for a particular patient's data. So then after training this classifier, if you feed the computer with a CT image with a CTV contour, and then the computer can tell you which physician did the contouring work. So the accuracy is about 85%, which is quite high. So that means even within the same department, following the same protocol, between the physicians, there's still a clear difference on the way how to segment CTVs. There's a strong personal style there. So we developed this deep learning framework to automatically delineate CTVs in post-op, post-cancer patients. The basic idea is to segment bladder and rectum and other organs first, and then using those segmented organs together with the CT images to help segmenting the CTV, and we have achieved quite good accuracy in this case. Then we also developed a method to estimate the uncertainty in the segmented CTV boundaries. Like in this case, the yellow region shows the 95% confidence level. So meaning we have this wide yellow region here. So that means AI is not very sure how to segment that part because the training data has variation from different physicians. That means some physicians, like in this case, some physicians may go into bladder more, some may go into the bladder less. So then the trained model is not very sure in this area, how to give you the boundary. And then with this uncertainty estimation method, AI can give you the answer, can also tell you how sure it's about this answer. And then the idea, the purpose for this work is to assist physician to review and to approve the AI contours, because we think physicians are still the final people to be held responsible, liable for AI's work. So we need to carefully inspect AI's work, and also finally we need to sign our own names to be responsible for that work to be used on patients. So we think, with auto contouring, there will be a lot of organs contoured. There will be a lot of CT slices. If you have to review every image slice, every organ one by one, it's going to be very tedious and also time consuming. So with this kind of estimated uncertainty, if we tell you, which part AI is very sure, don't worry about it. Which part AI is not very sure, has large uncertainty, and then you just focus on those areas with large uncertainty, then that can save you a lot of time, and it can facilitate the clinical implementation of AI. We also did the clinical evaluation of this work. So basically, we asked the 4 of our physicians to look at the 30 patients' contours, and each patient will be completely anonymized. And then we ask physician to give a score to this CTV contour. The score ranges from 1 to 4. 4 means this CTV contour is acceptable without any changes. We can use it directly on patient for patient treatment. And then 3 means acceptable, but with some minor changes. 2 means acceptable, can be used after major revisions. 1 is like totally unacceptable. So we present randomly an AI or a contour, CTV contour, um, in front of physician. This contour could be from AI or could be from a physician. And this physician could be yourself or someone in your group, another colleague of yours, right? You don't know that. And the patients were treated at least a year before this evaluation work. So now you give scores to those contours. And then what we found out, it's quite interesting. We found out you will give an average 3.4 to the contours drawn by yourself, and the AI 3.2. And then about 60% of the time, you will see, you will correctly identify this is a physician contour, this is not, this is the AI contour. So, but you are still wrong 40% of the time. That means 40% of the time you still think AI is better than human, right? So basically, between AI and your own contouring work, 3.4 versus 3.2, there's no statistically significant difference. Essentially, AI is about the same as your own work. Now, if you look at contours from your colleagues versus AI, you will give 3.1 to the contours drawn by your colleagues and 3.3 to AI. And only 25% of the time you correctly identified this contour was drawn by your physician. 75% of the time you thought this contour must be drawn by a physician, but you were wrong. It was done by AI. So basically, you are thinking AI is doing a better job than your colleagues. So then what do you do with that, right? What do you do with this kind of information? Because in this case, like I said, even though there is a clinical guideline, but on top of that, there's still room for clinicians to exercise their own practice style, right? So this is actually, I believe, the art part of medicine, right? It's not exact science in this area. So since there is no ground truth, actually we performed another study. We looked at the toxicity and outcome among all the 4 physicians, even though there were different styles for CTV joint, but there's no difference, no statistically significant difference in the treatment outcome or the toxicity. So in that case, how can you see which one is better, which one is worse? Of course, ideally, you can convince everybody to just use one grouply agreed style. That'll be ideal. But in practice, it could be challenging too, because everybody was trained at different programs, different institutions, and they have been treating patients this way for many years. They personally believe this is the best for the patients, and in the end, this patient is this physician's patient, right? So that's why we don't believe it's good to try to deliver unified contour from the AI to all the physicians, because that way, very likely each physician will disagree with that average contour and will manually revise it, and they found out that's too much work, and then they are not going to use AI. So that's what we believe. So we think the best way here, we call it human-centered AI. So that means we think in this case, AI does not give you the final ground truth, and we should respect physicians' personal practice style, and AI will be a tool to assist physician to encountering faster, better, right? So the workflow we designed here is to train the segmentation model, AI model, with the data you have. But when you deploy the data, you need to find out if the data is consistent with the local physician's style. And if typically it's not, then you should automatically adapt your model to this physician's personal style. And then when the physician uses this model for a new patient, and then by default, AI will give this physician his or her own style. However, AI will also present other mainstream styles. If the physician just click a button, they will say, hey, I'm not sure how to contour this part. I want to I want to see how UT Southwestern contours this patient if this patient were theirs. And then you just click a button. We show you how UT Southwestern uh, uh, would have contoured this patient. So you can look at also Emily Anderson style, Stanford style. Everything is there. It's very convenient for you to look at. And we believe this is also a learning process for less experienced physicians, for physicians in resource limited regions. So eventually we think with this tour, the contouring style will become more and more converged. Another important area of AI research in our department is treatment planning. So we use three types of AI technologies. One is called supervised learning to learn the relationship between the patient's anatomy and optimal relation dose. We use reinforcement learning to explore a large hyperparameter space to come up with a better treatment plan. And we'll also try to use imitation learning to learn from experienced planners how to do a plan. That is very similar to training AI to play video games or drive cars. So this is those prediction. We were the first to propose this idea and published a paper first on archive.org and then later on in scientific reports. So my colleague Dan Wen did this work. Basically, we use AI to learn what's the relationship between the patient's anatomy and the optimal dose relation dose distribution that this patient should receive, right? So after that, when there's a new patient, by looking at the anatomy, AI should be able to predict if you treat this patient with radiotherapy, this is how radiation dose distribution should look like, right? So we actually have done a lot of work in this area. You know, this is a head and neck VMAT case, and then we are trying to implement this in the clinic right now. Actually, we have implemented in the clinic. Our head and neck team is using this tool now. This tool will, you know, like I said, help planner and also help physicians that for this patient, this is the best you can do. This is how you should treat this patient. Therefore, the communication between the planner and the physicians will be much better. So, for example, the planner will not stop planning work prematurely. They know what's the goal, right? They know what's the best for this patient, right? They will also not waste too much time after we have reached the goal. After they have reached that optimal dose distribution, they know no matter how hard you work, there's not much room for you to improve, right? And also for the physician, they look at this plan, they will say, hey, this is what AI says we can do, the best we can do for this patient. Therefore, they are not going to push the dosimetries, try to do better. You know, there's not much better you can do anyway, right? So it can be very useful in the clinic practice. Also, it can be used to for auto planning. That's another project we're working on. So we found out the model you trained works nicely for you. Like in this case, We got data. We trained the model at UT Southwestern. Then we try to apply the data to a hospital in Europe. So if you look at this dose distribution, that's their clinical dose distribution for this patient. Using our model, you predict dose like this, which is quite different from their clinical practice. But we use a technology called transfer learning that can adapt our model to their practice very quickly. That's what we get in this column, right? So then you see this one and this one are very similar now. Then another work in planning is done by my colleague Jiang and Jiang. They try to use deep reinforcement learning uh, to, in this case, is for HDR planning. They try to use AI to tune these parameters, hyperparameters, to come up with an optimal treatment plan for the patients. Actually, demonstrate that AI can do better sometimes than physicians. They also apply the same idea to MRT planning, and they also have shown, yes, AI can do a good job, sometimes even better than human planners. And another work is to use AI for fast and accurate dose calculation. This is kind of like a new generation of dose calculation engine for radiotherapy, and we are also the pioneer in this area. Another application of the AI in radiotherapy is to optimal the treatment angles, beam angles. So we started this project several years ago. Uh, we tried to uh, actually we saw the energy between AlphaGo, that's the Go playing AI developed by DeepMind, Google, and we see between AlphaGo and our treatment machine here is CyberLife, the robotical radiotherapy machine. We saw there's a stronger energy. So in AlphaGo case, the AI tries to find out the optimal next move to win this game. In CyberLife case, AI tries to find out the optimal next move of the robot in order to deliver an optimal treatment for this particular patient. So we see these two, the analogy here between these two seemingly unrelated tasks. Then we used a very similar algorithm from AlphaGo to optimize the robot sequence of CyberLife. And we developed this AI software we call Deep Blue, stands for Deep Beam Orientation Optimization. We developed first version, and I can give you a good result very quickly. Second version, it can be also even better than the state of the art. And then currently we're working on the third version, which is good and fast. We actually also in the process of translating this work into our clinical practice for SBRT type of treatments, because in that kind of treatments, you want to deliver long coplanar radiation in beings. And we think this AI work can definitely help a lot to come up with the optimal beam angles. Another work done by our colleagues Jiang and David Scher is to use AI to identify the malignant versus benign cervical lymph nodes, so that if it's malignant, we need to deliver radiation to those lymph nodes during treatment. We finished this AI development, and also they have been doing a phase 2 prospective phase 2 clinical trial based on this work, which is quite pioneering in our field, an AI-based clinical trial. So this is a very interesting work. Another interesting work is to develop smart clinic based on AI. So we one thing we did is to a so-called RTLS, real-time localization system. So basically, we can track patients, clinic staff, and device equipment using this technology called Bluetooth Low Energy. So in our radiotherapy building, we have installed hundreds of Raspberry Pis. And for any patient, we'll give a small tank and also a staff. And then when the patient walks within the building, we can know where the patient is, in which exam room, in the waiting area, in the treatment board. Same thing for physicians, same thing for the device. So this is like an indoor GPS. Um, and it's kind of a mature technology, right? There are a lot of art is called RFID. However, the innovation part of our technology is based on AI, because if you just use Bluetooth Low Energy, which is very cheap, it's about two orders of magnitude cheaper than standard commercial solution. Like for the whole building, we only spend about $50,000 on the hardware. But then with this nice and cheap technology, the accuracy is not good at all because the Bluetooth Low Energy signal is not stable, is not a well-defined function as distance. If you just use the signal strength to look at the patients, there is a lot of uncertainty there, cannot be used in real clinical practice. So we use the deep learning AI to solve this problem. Actually, we make this whole system intelligent. So one example is if patient sits in the exam room, let's say by the wall, and then the signal will cannot the system the traditional system cannot tell the difference between this exam room and the next door exam room because the signal strength is very similar. And then you can see the system will tell you the patient is in exam room one, but next second the patient will jump to the exam two and then back and forth. It's very confusing for the users, right? So with AI, this kind of problem can be easily solved because AI has some intelligence there. It will say, hey, you cannot jump from room one to room two if there's no door between these two rooms directly. The patient cannot penetrate the wall, right? The patient has to go out of the exam room one into the hallway first, then get in the exam two. So this kind of intelligence can be learned from the training data. And then with that, and also a lot of things like that, we can achieve close to 100% accuracy with our AI-based RTLA system. Now we have been using this system in the clinic for a while now for many different applications. Like one application, like in this photo, the therapist holds a touchpad, and there it has this AI system there. A patient wears a tag, and also their accessories have tags like mask, like bed blocks, burners, and the machine has a tag. This room is tagged. So then when the patient walks in this treatment ward, the system knows it is the right patient at the right time for the on the right machine with all the right device there. Is there anything missing? So it's definitely very helpful to improve the patient safety with this technology. Another interesting application we call the PROMISE project, and it stands for Pediatric Radiation Oncology with movie-induced sedation effect. We started this idea many years ago when I was still at UC San Diego, and then we gradually make this technology working with AI and with the hardware software we developed. So basically, the idea is a lot of children patients they receive 25 to 30 general anesthesia during radiotherapy course in order for them not to move during the treatment delivery, which is quite tough for those poor kids. So what we did was we replace GA with movies, cartoons. So when the kids watch movies, cartoons, they don't move. In the meanwhile, we have a camera watching the kids. If they move, we'll stop radiation immediately, so there's no harm done. In the meanwhile, we'll pause the movie to tell kids, hey, if you move, there's a consequence. There's a negative feedback loop, right? So you need to learn not to move. The AI part of this is not just to detect the motion and also to predict the motion before the kids moves, and then there's some subtle signal on their face, on their in their eyes that AI can detect. This kid is going to move in a few seconds because he or she starts to lose interest in this movie now. You have to do something proactively, right? So that's the interesting AI part of this work. I think that's all I can tell you today. Our AI research, a few examples of our AI research at UT Southwestern. I hope you can join UT Southwestern as a resident, and then we can work together to develop new AI technologies, and also, equally importantly, to deploy what we have developed AI technologies to our patient care. Thank you very much.